Hi everyone, this is Professor Majumdar and you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started. Hello viewers, today I'm going to show CFD analysis and parametric study of a drone known as Genesis drone using SolidWorks flow simulation. In this parametric study, we'll consider the angular velocity of the propellers as the input variable, and based on that we'll go for optimization. Right? So without wasting time, let us start our analysis. So first of all, the flow simulation environment will be initiated from here, and next to that we need to start with wizard, and by default we are considering the project as project number 5 because before that we have already performed 4 different projects, and we are considering the unit system as SI as usual. Next to that, temperature is not that much important in this analysis, so as per normal practice we are considering temperature as degrees Celsius, and from load and motion we are considering angular velocity as revolutions per minute or RPM. Next to that, this will be an external analysis, and from physical features we need to select fluid flow, and it is dependent on gravity. Let us see the direction of gravity. It will be in y direction, you can see here. So along y it will be minus 9.81 meter per second square, and along z it will be 0. And as it is a drone, definitely this rotation will be required because in our analysis the propellers are the main part of this analysis, so we need to consider rotation, and we are considering local regions averaging. Next to that, gases, default gases it will be air definitely, and we are considering humidity also. We'll consider humidity with 65%. Next to that, we need to consider default wall thermal conditions and roughness, and finally from thermodynamic parameters, pressure will be 10135 Pascal and temperature will be 20 degrees centigrade. And in this case, velocity parameters, we can consider velocity at a specific direction also, but our main aim is to the movement of the drone in upward direction. Therefore in this case we need to consider velocity of air either in x or in z direction, but in this case velocity of air will oppose the movement of the drone. In this case we are considering 0 velocity. If we require, we can consider velocity in any direction of either x or z, but in our case we are not considering velocity of air. Okay, and from humidity, as I told before, it will be relative humidity with a 65% and temperature 20 degrees centigrade. And also we need to consider the coordinate system, as the drone will be moving in the upward direction, so coordinate system will be along y direction. So let us finish this one. Now we can see our computational domain. It is ready. You can see computational domain is being generated. It is recognizing fluid domain or fluid volume. So this is the computational domain. You can see that we need to reduce the volume of this domain to reduce computational time. We are having 4 different propellers or rotors. Here 2 propellers will be moving in clockwise direction and other 2 will be moving in anti-clockwise direction. This is equal to balance the torque. This is counterclockwise or anti-clockwise. The red ones, these 2, this one and that one, will be rotating in anti-clockwise direction. This one and that one, this blue colored one, will be moving with clockwise direction with specific RPM, right? Okay. Another thing is, in this CFD aerodynamic analysis, for any rotating component, we need to put some kind of dummy spaces. We have already made this one. Let us show that one. You can see here, back side, we have created 4 numbers of dummy spaces, and we have made that one hidden at this moment. Let us show it. From solid bodies we can show it. This one is hidden. Let us make it visible. This one, second one visible. We made all the dummy spaces visible, right? Now you can see here four different rotors or propellers are there. Two will be moving in clockwise direction and other two will be moving in anti-clockwise direction. This is required to balance the torque, right? Now while performing this CFD analysis, we need to provide these angular velocities from here. Like we need to provide initial condition, that is at which velocity these rotors will be moving, that to be provided from here itself. So rotating regions to be specified from here, right? This one, it is clockwise rotation. So you can understand that blue one is for clockwise and red one is for counterclockwise. You can see here it is. The first one, we need to provide a rotation of 1000 rpm. Okay, so let us provide this one 1000 rpm. Now we need to select that spaces or these dummy spaces. You can select it from here. So this is clockwise rotation. You can see here it will be moving with a angular velocity of 1000 rpm. Okay, done. Second one, this one also will be moving with the same angular velocity of 1000 rpm. So again, inserting rotating regions, select the second one and it will be also moving with the angular velocity of 1000 rpm. Done. Now other two, so this one and that one will be moving in counterclockwise direction or anti-clockwise direction with the same angular velocity, right? So insert rotating regions. Let us select that dummy spaces. This one will be moving in anti-clockwise direction, so it will be minus 1000 rpm. You can see the direction is counterclockwise. Okay, go and check. Now the last one, insert rotating regions. You need to select this one. This one also will be moving in anti-clockwise direction with a angular velocity of 1000 rpm. So minus 1000 rpm specified. Done. So the angular velocity is provided to the rotating dummy regions. Next to that, we need to provide some kind of goals, right? As rotating regions have been defined, so we can make these rotating regions hidden again. Done. And in this analysis, we need to see whether this drone is capable of moving up or not. That can be also checked using this CFD analysis. Because for this movement of this drone, we need to have some kind of upward thrust or upward force is required. And if the upward force is more than the weight of the drone, in that case, the drone will be capable of moving up, right? So that one can be checked from here itself with some different goals, right? So starting from goals here, insert global goals. Initially, we'll select two global goals. That will be mainly the pressure difference, maximum and minimum total pressure we are finding as global goals. The difference of this pressure is actually responsible for the movement of this drone. So first goal as a global goal we have selected. Next to that, we need to select some kind of surface goals. That means how much thrust will be generated, that can be seen from these goals. So insert surface goals. Here we'll do one thing, like we'll see the thrust provided by this pair of rotors in the upward direction. By the same time, we'll see in the downward direction also, right? So what can we do is we can select some specific goals in a different way. It will be force in y direction because it is moving in the upward direction. This is actually known as counterclockwise. So we can select this one, up, down, both up are selected, and again this one, upward blade we have selected, green check, and we can rename this one as thrust on upward blades, counterclockwise thrust. Again, we need to select thrust for the rotors which will be moving in the clockwise direction. So goals, insert surface goals, and we need to select force in y direction, and we need to select this one and this one. These are actually moving in clockwise direction, selected. So these two will be representing thrust in the upward direction by the rotation of rotors in clockwise direction, right? So green check, and we can rename this one as clockwise thrust on upward blades. Done. Now we need to select the same thing for the downward blades also. So again we can select surface goals from here, insert surface goals, and again it will be force in y direction. So we can rotate this one. You can see this is clockwise, so select the downward part of this one. And this is actually clockwise one, so green check, and we can rename this one as clockwise thrust on lower blades. Clockwise thrust on lower blades. Done. Next to that, we need to select for the counterclockwise blades. Again, goals, insert surface goals. We need to select the counterclockwise one. First one selected, second one, and the other one also selected. And from here we need to select force in y direction. Green check, and we can rename this one as counterclockwise thrust on lower blades. Done. Right? Okay. Now we need to consider some equation goals to find out what are the upward thrust and also lower thrust. And by adding all these goals, we need to find out the total thrust. And finally, as an equation goal, we need to select net thrust in the upward direction, and that will be done by subtracting the weight of the drone from the total thrust. Right? So insert equation goal, and from here we can add all the goals. These thrust values will be positive, so as an equation goal we need to consider this one as an absolute one, right? Counterclockwise thrust on upward blades plus absolute of clockwise thrust on upward blades. Done. Green check. This equation goal can be renamed as total thrust on upward blades. Done. Now another goal should be equated to find out total thrust on the lower blades. So goals, insert equation goals, and we can select the goals from here. Again, like the previous case, we need to consider the absolute values of all these things. So absolute of clockwise thrust on lower blades plus absolute of counterclockwise thrust on lower blades. Done. Green check, and we can rename this one as total thrust on lower blades. Done. Now finally, we need to find out the total thrust, that is total thrust on upward blades and total thrust on lower blades. Again, you can select some equation goal from here, insert equation goal, and goals can be selected from here. Let us add these two different goals. First one plus second one, total thrust on lower blades. Done. Green check, and we can rename this one as total thrust. Done. Now the thing is, we need to see that whether the drone will be capable of moving up or not. If total thrust is less than the weight of the drone, in that case it will not be able to move up. So net thrust should be more than 0, right? So we need to select another goal, that will be net thrust. Insert equation goal. Let us what goes from here. It will be total thrust minus weight of the drone. The mass of this drone is actually 142 grams, so it will be 0.142 kg multiplied by 9.81 Newton. Done. We can rename this final goal as net thrust. We need to see that this net thrust should be definitely more than 0. If net thrust is less than 0, in that case drone will not be able to move off. Okay, so all the goals are decided. Next to that, we need to mesh it. We can select automatic mesh, and level can be increased up to 7th for better accuracy. And we are considering uniform mesh, advanced channel refinement, and also we want to see basic mesh, right? So this is the mesh distribution, you can see. Done. Green check. Now we need to run this one, right? We have already done this one in project number 1, so we can see the results from project 1 itself. right? Let us go back to project 1 and see the results from different cut plots and also from goal plots. We need to load the results from here. Let us load it. Results are loaded. First of all, we'll see different cut plots of pressure and velocity from different planes. So results, and we need to select some different cut plots, right? So insert cut plot, and you can view it from different planes. First of all, we'll see from this plane, and the display pattern will contain contours, isolines, and also streamlines. And we want to see pressure distribution, right? So green check. This one is showing pressure distribution. Now it will be better to see in the form of an animation. So let us play this. This is pressure distribution from top plane. Better to see this from actually front view, right? You can see this one. Let us clear and hide this one, and we'll see from different planes, right? Clear and hide, and we'll view this one from different planes. So again, insert cut plot and edit definition. We'll see from different planes, right? So change the plane from here. Initially it was from XY plane, now we'll see from XZ plane, right? So green check. This is the distribution from the given plane. Now you can view it in the form of an animation, right? So cut plot 2, let us play. You can view it from top plane. You can see here some vortex motion is created at the centers of these different rotors or propellers. Now we can change this pattern. Instead of pressure, you can see velocity also. Let us change it from pressure to velocity. So this is velocity distribution from top plane. Let us clear and hide this one. And we will see from the remaining plane again. So cut plot 2, edit definition, and we want to view it from YZ plane. Green check. So let us change the orientation. This is velocity profile, right? You can change it to pressure also. Let us change it to pressure. Let us play this one. This is pressure distribution from the remaining plane. From these different cut plots, it is not clearly understood, but from dynamics of flow particles, you can see how the flow particles will be moving and creating vortex at the centers of these rotors, right? So let us clear and hide this one. Next to that, we want to see surface plots, and we want to see pressure distribution throughout the all body of this drone. We'll use all faces. We'll see contours of pressure, and by the same time we'll see isolines and streamlines also. Green check. This is the distribution you can see. This is pressure distribution. You can see rotors, we are having different colors indicating different pressure zones. and throughout the whole body you can see pressure is almost constant. It is in the yellow zone indicated by 101,319 Pascal. So pressure distribution, it is almost constant throughout. Little bit of difference in pressure is visible at the propeller top sides, right? So let us clear and hide this one. Next to that, we will see the most important part of our analysis, that is dynamics of flow particles. So insert flow trajectories, and we want to view it from top plane. In this case, numbers of points, instead of 20 numbers, we will make it 50. And when you see pressure distribution, right? So green check. You can see, as I told before, some vortex motion is created at the centers of these four rotors. So as I told before, these are the four different propellers, and surrounding these propellers some vortex motions are created. Let us view the dynamics of flow particles right now. Let us play it, and also it will be easier to see from front side. Let us see it, how the flow particles are moving from top to bottom. Flow particles are moving from top to bottom, and here some kind of vortex motion is created, and some of the particles are moving down, and that is creating actually thrust. If we increase the numbers of particles, then it will be clearly visible. Let us increase the numbers of particles, edit definition, and instead of 50 numbers, let us make this one 100 numbers of particles. Green check. See, more numbers of particles are actually coming down, and that is actually creating up thrust. Let us play this one. So at the four centers of these propellers, some vortex motion is created. And from this one, we can see that thrust is not that much of produced. We cannot see that much of thrust is produced because less numbers of air particles are coming down. And those particles which are coming down, those are producing actually thrust. So in this case, thrust produced is not sufficient enough to move the drone in the upward direction. That one we'll see from the goal plots, right? So let us close this one. Next to that, we'll see our most important part, that is goal plots, right? So clear and hide this one, and goal plots. Insert goal plots. We want to transfer all these goal plots to Excel. So exporting these to Excel, and we'll see it one by one from there. Let us view this one from Excel. This is all the data in the form of summary. Next one is net upward force. That means it is the total upward thrust minus weight of the drone. It should be actually positive. It is negative, which means what I told is perfect one. That means the force generated in the upward direction is not sufficient enough. It is less than the weight of the drone, so the drone will not be able to move in the upward direction. So you can see here, after 134 numbers of iterations, net upward force is 1.244 Newton, which is very less one, right? Next one is total upward force. This is the addition of clockwise and counterclockwise one. This is lower blade force. After 134 numbers of iterations, it is 0.0107 Newton. This is very less. Next one is upper blade force. This is again 0.137 Newton. This is very less. And this one is clockwise lower blade force. This is also very less, 0.005 Newton. This is counterclockwise lower blade force. This is also very less, minus 0.054 Newton. So you can see here, all the force generated, it is not sufficient enough to move the drone in the upward direction. So we need to change the input variables. That is, we need to change the RPM of the rotor or RPM of the propeller to produce huge amount of thrust, which will move the drone in the upward direction, right? You can check all these things later on also, right? Let us close this one. You can see all the results from here also. Let us show it in the form of Excel also. You can check it, right? Or you can see it from the history as a graph. These are all the goals what we obtained, right? So from this analysis, it is evident that net thrust or net force is less than 0. It is negative. That means total upward force is less than the weight of the drone, so it is not capable of moving up. So for the upward movement of the drone, we need to provide more thrust, right? And we need to have the net thrust to be positive. For that one, we need to increase the RPM of the rotors or RPM of the propellers, right? Next to that, we will perform different set of analysis with the different RPMs and see what are the results, right? Next one, we have performed another analysis. This is known as project 2. Let us see what we got. Now in this analysis, we will not see the dynamics of flow particles. We will see only the results as goal plots. We have run this one with a different velocity. In this case, we have run the propellers with 2000 RPM. Let us see the results. Results loaded. Now you can see it from here. Goal plots. Insert. We want to see all the goals from here itself. Let us show it. Our main aim is to see the net thrust or net force, right? You can see here the net thrust or net force is 0.859, but it is negative. That means net upward force is not sufficient enough to move the drone in the upward direction. That means when you are moving the propellers with a angular velocity of 2000 RPM, then also it is not capable of moving up. That means we need to run the propeller with more angular velocities, right? Let us close this one. Next one, we'll see the different analysis. That is the third one. We increase the angular velocity to 4000 RPM. All the velocities you can see, all are having 4000 RPM. This is counterclockwise and this is clockwise, right? And let us see the results. Results not loaded. Let us load it. Results loaded. Now you can view the results from here in the form of goal plots. Insert goal plots and you want to see all the goals from here. Let us see it. So in this case, angular velocity is actually more. It is 4000 RPM. And again, our main criteria should be to see the net thrust or net force. We can see here net thrust is positive. It is 0.699 Newton. It is very less, but it is sufficient enough to move the drone in the upward direction. But if it is more, then it will be better one. So we need to run the propeller with more than 4000 RPM, right? Let us close this one. Finally, we'll see the fourth project. In fourth project, what we did, let us see the RPM of the rotors. It is 6000 RPM. This is counterclockwise rotation with 6000 revolutions per minute. This is clockwise motion with 6000 RPM, and this one is also clockwise. Now let us see the results from here. It should be loaded first. Done. Now you can see the results from here. Goal plots. Insert goal plots. We want to view all the results from here. Let us see it. And again, as I told before, our main point of attraction is to see the net force or net thrust. You can see here, when the angular velocity is 6000 RPM, in that case, the net thrust is 3.387 Newton. It is good enough, but again, we need to increase this value. To have better balance over the drone, we need to have more values of this net upward force, right? So this is good enough. Now, instead of doing this different analysis one by one, we could have done this one as a single parametric study and could have generated more data, right? Now we'll see that one, how to generate more data with a different set of angular velocities, right? Okay, so for that one, we have to perform another analysis that is known as parametric analysis, right? We'll not complete this one. I'll show how to do this one, right? For starting this parametric study, what we'll do is we'll start from here, solve, and it will be new parametric study. And from here, we need to select design of experiments and optimization. And we need to provide input variables or the data from here itself. The data can be obtained from these general settings or from rotating regions, right? That means the velocity of the propellers can be selected, or from general settings, we can change the initial conditions. Let us consider rotating regions. That means we want to increase the velocity of these propellers. So we can select all the parameters like this one. angular velocity of the counterclockwise motion of the first rotor. We can select all the parameters. That is counterclockwise motion of the second rotor. This one is clockwise rotation of the first rotor. Again, this one is the last one, that is clockwise rotation of the second rotor. We're considering all the blades. Run check. Now the thing is, we have already specified in the last set of analysis that the RPM of the rotors was actually 6000. Now in this case, you need to specify the RPM. Based on this specified RPM, software will perform a huge numbers of simulations and will get huge numbers of data as per our requirement, right? Let us make the rotation of the blades as 10,000 RPM. So this one will be starting from minus 10,000 to minus 6,000. This is the counterclockwise one. Second one also will select the range. It will be minus 10,000 to minus 6,000. And for clockwise one, it is positive. So we can select from 6,000 to 10,000. Done. And the last one also, this is for also clockwise rotation of the second rotor. We can specify this one again, 6,000 to 10,000 RPM. Done. Selected. Now what we have to do is we need to select output parameters. That means what we want to find out, and that can be obtained from here. Adding goals, we can select all the goals. Done. Now let us see the scenarios. It will create 20 numbers of experiments. Let us create this one. See, at a different RPM, we can have different set of results, right? So 20 set of experiments will be generated. It has selected different RPM of the different rotors, but we can change this one as per our requirement, and we can perform this parametric study with 20 numbers of experiments. Instead of 20 numbers, we can make it more. That is up to our requirement. So with different RPM of the different rotors, we can get different values of our goal plots, right? We are not doing this one. We can do it later on. Okay. This way you can do our parametric study. Let us close this one. So this is all about our today's analysis. This was a very simple analysis of a Genesis drone using SolidWorks Pro Simulation. In this analysis, we have seen whether the drone will be capable of moving up or not. And we have seen different goals at different RPM of the propellers. Initially at 1000 RPM, the drone was not capable of moving up. In that case, the net force was negative. In the second case, when the rotor was moving with 2000 RPM, in that case also, the net force was negative. And in third analysis, when the rotor was moving with an angular velocity of 4000 RPM, in that case, we could see that net thrust was positive. And finally, at fourth experiment, we could see that when the RPM is 6000, in that case also, the net thrust is positive. So from this analysis, it is evident that we should have a better control of the angular velocities of the propellers to control the drone. Because if we are trying to move the drone in the upward direction, in that case, angular velocity of all the propellers will be same. But if we want to move the drone in the backside or front side, in that case, the RPM of the rotor should be varied, right? Okay. So with this one, we will conclude our today's analysis. Thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.